Hello and welcome to the first section in Chapter 3. So Chapter 3 is about shortcuts to differentiation. That is the name of the chapter, and it's a good chapter title because it's shortcuts because you can avoid doing derivatives algebraically, meaning using this limit definition of the derivative, the limit of the difference quotient as the change in x or h approaches 0. So because that gets really messy, especially if you have functions that where you can't really simplify this, if you have weird trig functions or there's all kinds of ways it can be really difficult. So we want to avoid doing those kinds of difficult problems. But first, to warm up, we're going to do this first problem that way. So remember, finding a derivative algebraically means using the definition of the derivative. Also, meaning the limit of the difference quotient. Also, the d over dx, just a reminder, means just the derivative, or the derivative of whatever's after it. So this means the derivative of the function 3x plus 2, and that's another way of just saying if your function is f of x equals 3x plus 2, find f prime of x using the definition of the derivative, the limit of the difference quotient. And then warm up 2 is about some of the first derivative rules you learned in section 2.3. We're going to go over those again in this section, but it's good to look them up and check these here. So now let's pause it and do these because the answers will appear in 3, 2, 1. So with the first one, using the limit of the difference quotient definition, you just plug in x plus h and plug in x and subtract those results. Most of the stuff cancels out, and then you end up with 3h over h, and the h just reduces because it doesn't matter if h equals 0, and you just get 3 as your result. So the derivative is 3. That agrees with the answer to warm-up number 2. Part B, where the derivative of any linear function is always just whatever the slope of that function is, which in this case m was 3. Now, for A, the derivative of any constant function is 0, and the derivative of any power function, like this, is just n times x to the power n minus 1. And here's a couple quick drawings to help illustrate A and B here. With A, if you just have a constant function, the derivative of just y equals k, or f of x equals k, is just always equal to k, whatever that y coordinate is. So the slope of that is always 0, and of course the slope at any point of any linear function is always constant, so that's m there. Let's look at some more differentiation shortcuts, what this section is really about. Here's our first theorem that we're actually going to prove in just a second. But first, what it says is that if a function's derivative exists, so meaning if f of x is differentiable at the values of x you're talking about, and c is a constant, just some number, then the derivative of this function, which is c times that other function, is just equal to c times the derivative of the first function. So what I want to do is just do a quick example of that and then check that we could maybe do this without the theorem if we wanted to. So we're going to actually do this problem two ways. You don't need to pause it for this unless you really want to, because I'm just going to explain it here. So for part A, without using theorem 1, when the function that we're taking the derivative of is 3gx, then I can just rewrite that 3gx as 3 times negative 2x plus 1. And then once I just distribute the 3 here, just finding out what this function is, 3 times gx, then you see that you just end up with negative 6x plus 3, which is just a regular old linear function. And using the rule from before, the derivative of any linear function is just always equal to its slope. So this is just -6. Okay, now to do this using the theorem here, just to check what this says for part B here, that would look like so. So the function that we're differentiating here, 3 times g of x, is of this form. It's a constant times another function. So you could use this rule to say, well, according to this theorem, I can just take the 3 out and then multiply that by the derivative with respect to x of g of x. And then g of x we can replace with its formula, -2x plus 1. And then the derivative of that, using the same rule as before, that the derivative of a linear function is always equal to its slope, that just becomes 3 times -2, and so your answer is still -6. Just like it was before. So the rule works, at least with this function, and this is a method, sort of approach to learning differentiation that I'm going to recommend, that you try to do every derivative as often as you can. Try to use multiple rules. See if there's more than one way you can do it. Because you are getting twice as much practice that way, and that's good, but it's worth more in terms of understanding the rules and remembering them for longer it's worth more than twice as much as just doing one problem if you try it 2 ways, because you can really understand how the rules work and how they can apply to a lot of different situations and really understand them better. So I'm going to emphasize this as we go forward, that you want to try doing things in more ways than one as often as you can, especially with these derivative rules, because there's going to be a lot of functions that we see where there's like 3 or 4 different ways of approaching it. And if you always use the same method all the time, you're not really going to stretch yourself and get better with newer, different kinds of derivatives that you might not have seen before. So anyways, let's prove this fact really quick here. We start by just assuming that the stuff that is after the if is true with any proof that's like an if-then statement. So assuming that part, let's just use all of the math we know, all the stuff we've proven before, to prove that this other fact over here might be true. So to prove anything about a derivative, you really need to rely on the definition of the derivative as the limit of the difference quotient, which is this. So if the function that we're differentiating is c times f of x, then we just need to plug in x plus h into that function, c times f of x plus h, and then also plug x into it and subtract. And then we want to use whatever math we can. We want to get this result on the right. We want to show that this whole thing is equal to this. That's the goal. So what we can do is start by factoring out the c from the top of this, like so. And then there was a fact from one of the limit laws before said that if you have a constant multiplied by another function and you take the limit of that, then that's the same as doing the constant times that limit. So in other words, you can take the c out of the limit like so. And when you use that limit rule to factor out, you're allowed to do that because this limit on the right exists, and it has to exist for you to do that. And how do you know this limit on the right exists? Well, because we assumed that it was a differentiable function in the beginning. So this is just the same thing as getting c times f prime of x, which was the goal, was to show that this nice check stamp. Ooh, I can make a star. Yay. Anyways, it was to show that this derivative of c times f of x is the same as doing c times f prime of x using the definition of the derivative and one limit law along the way. Anyways, let's look at one more theorem here we're going to need. So this one says that if f prime of x and g prime of x both exist, then the derivative of the sum of those functions, f of x plus g of x, is equal to the derivative of one plus the derivative of the other one, and it also works if it's subtraction. So assuming both of these derivatives exist, the derivative of f of x minus g of x is equal to f prime of x minus g prime of x. So let's just do an example of that. You might want to try this one here first, using the rules we've learned on your own, just to get a little practice. But if you're going to do that, pause it now, because the answers will appear in 3, 2, 1. Okay, this is the answer, 2x minus 3. So yeah, I took the derivative of the x squared separately from the derivative of the 3x, and then just subtracted those results, like this says I can do. So the derivative of the x squared is 2x, the derivative of the 3x is just 3, and you then just subtract them, and that's your derivative. And this is actually, these two theorems together are kind of interesting, because they say that derivatives work kind of the same way as multiplication by numbers does. Like, for example, if I was doing, I don't know, 4 times 7 times 3 minus 2 or something like that, I just want to do an example of things you can do when you're multiplying by 4. Whoops. Okay, so one thing you could do is you could distribute the 4 in there. So you could do 4 times 7 times 3 minus 4 times 2. And then you could, if you have 4 times 7 times 3, of course you could write that as 7 times 4 times 3 minus 4 times 2 if you wanted. And so you can do stuff like that with numbers. This theorem and the one before says that that works with derivatives too. So like if I have, let's say, d over dx, which, remember, this isn't really a number, but if you write it like this, d over dx of something, and it looks kind of like multiplication, with, for example, let's say 7 times x squared minus natural log of x. So we just have some function here with multiplication by a constant and subtraction between them. You could do the same thing here. You could do the derivative of 1 minus the derivative of the other one, is what this is saying. And then the derivative of 7 times x squared, of course you could use the other rule there and write that as 7 times the derivative of x squared. So it works kind of like multiplication with numbers does, is what I'm trying to say here. And this is actually an important thing when you get into more advanced kinds of math. We say that that differentiation is an example of a linear operator, and you study other linear operators a little bit in linear algebra. it just does things to functions instead of just to numbers, the way multiplication by numbers do. Anyways, let's prove this derivative of sums and difference things real quick. So to do it, we're going to do the same thing, just assuming that f prime and g prime exist. Then use the definition of this derivative on the left to show that it must be equal to the derivative on the right. So yeah, starting by assuming that f prime exists and g prime also exists. We're going to need that fact in a minute. And just using the definition of the derivative here, I wrote out what this is defined to be. It's the limit of f of x plus h plus g of x plus h. So it's taking our function that we are differentiating here, our original function, and plugging in x plus h, and then minus what you get when you plug in just x and subtracting, and all over h. And then you see we can put the f of x plus h minus the f of x, we can put that one together, and then put the g of x's together, and you get this result. So I did the f of x plus h minus f of x, and that was all over h, so I just put that in a separate fraction, and then I put the positive g of x plus h in the minus after you distribute that minus in there. So that gives you this other thing. And of course you can write them as both over h here, because if you add them together, they have the same denominator and they would just combine into one big combined numerator all over h. And now at this stage, we know that the limit of this part as h approaches 0 exists and is f prime of x, because we assume that exists, and then we also assume that the g prime of x exists, so therefore this limit must exist and it is g prime of x. So that gives you the result we wanted, which is this is f prime of x plus g prime of x from here, and that's the proof of this theorem. Okay, let's see one more super important rule. We already learned this one before, but before we were just looking at, I believe, when n was an integer, if I'm not mistaken. It turns out it works with any real number. We're going to skip the proof here because it turns out it's not that hard to prove it for integers. If n is a whole number, like 4 or -7 or something like that. And then it's not too hard to prove it with rational numbers, although it takes a bit longer. You can prove that it works if n is, like 4/7 or 5/2 or some fraction like that. If it's involving square roots, that's not too hard to prove. What it's really hard to prove is, like, what if you have x to the pi? Like an irrational number there for the n. So yeah, it turns out that the derivative of x to the power pi is pi times x to the power pi minus 1, which is weird, but it works. And because of the fact that it's so weird for things like this, and it's a pretty long proof, we're going to skip the proof. It would take, all day long, another hour of watching this video to get all of it done. And we got other stuff we have to concentrate on for this class. If you're a math major and you take a real analysis class in the future, you'll be proving all kinds of stuff like this. You won't be able to skip the proof in that class. Anyways, let's look at an example here. These get progressively harder, I think. Don't bang your head against the wall with these examples as usual, but you should try them. And let's pause it now and try it, because the answers will appear in 3, 2, 1. So for the first one here, I'm just using 2/3 as the n, so you get n times x to the power 2/3 minus 1. And 2/3 minus 1 comes out to be negative 1/3. So that's the result. With this one, the only trick is that 1 over t squared is the same as t to the power negative 2. So you just have to write it that way first, because we don't have an actual rule for what to do with this fraction. So you just have to write it as to a negative power here. Then just applying the rule, multiplying this by 4, and then 4 minus 1 is 3, multiplying this by negative 2, and then negative 2 minus 1 is negative 3, so that's that result. With part C, the first trick is that we don't have any differentiation rules for square roots explicitly, but every square root is actually just x to the power 1/2. So if you just distribute that in, you add up the exponents, so the exponent 1/2 plus this exponent 1 gives you this 3/2, and then just x to the 1/2 times 1 is x to the 1/2, and then those are the exponents you can use now with the power rule, and that gives you the 3/2 in front here, and then the exponent is 3 over 2 minus 1, which comes out to be 1/2 in the end. And the other one, the exponent is 1/2, it goes in front, times x to the power 1/2 minus 1, which comes out to be negative 1/2. So you got that. With D, the first thing I did was I split it into two separate fractions, which is the same here, because if you add them up, you just get that square root of z is the same in both the bottom and the top, so you can just combine those fractions and get the same thing here. So then you have z to a power divided by z to a power. You can subtract those exponents to get the new exponent when you divide. So our function that we're differentiating now to get it into form that the power rule can deal with is this, 3z to the 3/2 plus z to the 1/6 power. And I just noticed a big mistake here. Did you notice the mistake? The mistake is that when I applied the power rule here to do this derivative, I have 1/6 in front, and then the exponent is 1/6 minus 1, which should be negative 5/6. So if you got that correct when you did it on your own and noticed I got it wrong, give yourself a big pat on the back. And yeah, so those are kind of tricky, but this is a thing that things like this might be tricky right now. Hopefully you'll get a lot of practice. You might be rusty with some of your exponent rules we used here, but hopefully those should come back to you. And next, I'd like to talk about tangent line approximations. Again, we've already talked about these before, but this is a good place to talk about it because there's kind of space in this section to have some more problems that are about tangent line approximations. So, first of all, I want to, and this is an important enough thing that we want to spend some time on it because we're going to use tangent lines a lot, and it helps understand a lot of things in calculus to know how slope works. So anyways, let's suppose that you have a function that is differentiable at a specific value of x, we're going to call a, and then we have other values of x near a. So for example, if your a was -1 here, and your x was -0.8, then if we just knew about the derivative of this function, but we didn't know any other, we didn't know about the other values of the function, like we couldn't just plug in any old number we want for some reason, which happens a lot of the time. In that case here, if we want to estimate f of -0.8, let's say, f of -0.8, well, it's not that close to f of -1 because the function is increasing so steeply here. In fact, this actually has slope 7, I set this up so I know that it has slope 7. So because it's so steep, if you just move over a little bit in the x direction, then the amount that you move in the y direction here, that delta y is going to be equal, or I should say is approximately equal, to the slope times the change in x. Now, when I say approximately, let's go back to what I was saying here, so we can keep the notation straight, because that's what's, I think, the hardest thing about this, as long as you understand slope, is keeping the notation straight. So let's make a new function, what we're going to call L of x, which is this tangent line here. So L of x is the line, and f of x is the original function itself. So how do we get L of x? Well, we're going to remember our old friend point slope form, which says that if a line has slope m and a point x1, y1, then point slope form says it has this equation, y equals your y1, your starting y coordinate, plus the slope times the change in the x coordinates. This whole x minus x1 thing here, remember, is your delta x, and the m times, what am I doing? This whole thing, go trying to make a big brace there. After you multiply the slope times the change in x, you get your change in y. So just reminding you of that principle, that multiplying a slope times a change in x gives you your change in y. So for example, if your slope is 7 here, then and you increase your x coordinate by 0.2, then the change in y would be about 1.4, which is about what it looks like here. That's 0.2 times 7. Okay, so what does that look like in this case? Well, with our linear function here, L of x, well, the x1, y1 point that we know about is the point on the graph itself. So it's tangent at this point, a, f of a. So our a is -1 and our f of a is -3 in this case. So that's what our y1 is that starting y coordinate, f of a. And then we're going to add to that the slope of the tangent line, and the slope of the tangent line is just the derivative of the function at that value of a. And then if we multiply that by our delta x, or in this case x minus a, because we're, again, the specific point we know about right here, that point there is a f of a, so that's your x1, y1. And again, you always just want to think of this as like the starting y coordinate, and then this whole thing is the change in y. And so this is really useful because if you take a value of x that is really close to that value of a, then this becomes very, very precise. It becomes you can barely tell the difference on this graph for values of x close to -1 here. The difference between the curve and the line, and that difference becomes 0 the closer that the point gets to the line. anyways, so in other words, L of x is approximately equal to f of x. So you could say that this is approximately f of x, as long as x is near a. So let's use that to answer a question here. If we're just given 1 point on the graph, if we just know one function value and we know the derivative, how can we use that to approximate f of 5.03? So we're just going to use this. We're going to say, well, f of 5.03, well, it's approximately what you have when you start at 3, so we're going to take that starting value, and then f is changing at a rate of -2, so I can write -2 times whatever the change in the x direction is, which is 0.03 from here to here. So that's the 5.03 minus 5 here, and you get 3 minus 0.06 is 2.94, I believe, and that's an approximation for f of 5.03. And yeah, and that is using this rule. Basically, this is our f of a value there, -2 is the f prime of a there, and then when you do 5.03, our value of x, minus our value of a, that's what you get, is 0.03. Okay, here's another example. For what values of x is this function both increasing and concave up? So I'll give you a big hint. This is a hard problem if you want to do the whole thing yourself. But to see where it's increasing, that's going to be where the first derivative is greater than 0, or maybe equal to 0. And it's concave up basically where the second derivative is greater than 0. So we want to see what values of x make both of those things true, and let's pause it here because the answers will appear in 3, 2, 1. Oh boy, that's a tricky one. Well, here's the solutions. I hope you didn't hurt yourself doing that. There's a few tricky things along the way. Anyways, the answer is when x is greater than 1 is when this is increasing and concave up. So first, you have to actually find the first derivative, and I did that using the power rule here. The derivative of x to the 5th is 5 times x to the power 5 minus 1. The derivative of -5x is just -5, and you can do those separately because they're just separated by minus. And that's greater than 0. When this is an increase, when the original function is increasing. So I just add the 5 to both sides, divided everything by 5, and x to the 4th is greater than 1. That doesn't just mean x is greater than 1, although x greater than 1 will work, because this is an even power. If x is less than -1, that will work too. So for example, -2 to the 4th power is +16, and so I just like to think about this kind of thing by looking at a graph like this. There's values of x over here and values of x over here on your graph of y equals x to the 4th. So that tells you when the first derivative is positive. And over here, the second derivative comes out to be 20x cubed minus 0, and that is just basically x cubed is positive whenever x is greater than 0. The graph of an x cubed function looks like this, because you can only cube a positive number and get a positive result. If you plug in a negative value of x, then x cubed is negative. Yeah. So that's just when x is positive. So when is the original function increasing and concave up? Well, both of these things have to be true. So the x is less than -1 doesn't actually work here. So we need to have x greater than 0 because of this. So the only part that we get is where these two sets overlap is when x is greater than 1. Okay, here's a couple of practice problems to try, or maybe 3 depending on how you count it. These first ones, or one here, is just doing the derivatives of these functions using, you might need to remember the fact that the square root of x is the same thing as x to the 1/2 power for those. And then for this one, use the fact that 2.99 is close to 3, so f of x is approximately linear, so you can use a linear approximation to find this. And pause it and try these now, because the answers will appear in 3, 2, 1. And here are the solutions. So for h of w, I started by rewriting the function like this, just taking the square root and writing it as w to the 1/2. And same thing over here, the square root of t is t to the 1/2, and 7 over t is the same thing as 7 times t to the -1. And then just using those, the power rule mostly, and also just taking the derivative of each of these terms separately using theorem 3.2, you can just take the derivative of the first term plus the derivative of the second term here, and it should all work out like that. Anyways, for problem 2, I'm just using this approximately linear formula, which is basically the same as point slope form. So your starting y coordinate plus the slope of the tangent line times the change in x, which with these numbers, f of 3 is -4, plus the slope is -2 times -0.01 to go from 2.99, or from 3 to 2.99, is -0.01 is a change in x. Anyways, that comes out to -4 plus 0.02, which is -3.98. So, sorry about that mistake. But anyways, good job sitting through this whole lecture. I think this might have been kind of a tough one. This rule will become easy once you get enough practice with the square roots and with the fractions. It will become easy, and it will become quick to do derivatives like this. These will become our basic derivatives. And later on we'll learn some more shortcuts for more complicated functions. Like, what do you do if you have sine of the square root of e to the t squared? I don't know. Big messy functions like that we'll deal with in other sections here. And let's get lots of practice and be ready for class, hopefully, and I'll see you then.